Hello everyone, welcome back to the course on architectural design of ICs. So, in the last class we are seeing that the issues which are related with timing closure, that means whenever we are doing this digital VLSI design. So, at that time we have to do this timing analysis. So, static timing analysis only we have only considered, we have not set or we have not seen this dynamic timing closure at that time or dynamic timing analysis, but the concept of dynamic timing analysis is that we have to put the timing that means the some set of or selected set of input vectors and then we have to do this timing analysis. Okay. So, as that is simulation based, so that is why that means you have to need the simulator to do that on the real time or that perform the dynamic timing analysis, you need the logic simulator too, not only the timing analysis tool set. Then today again we will talk about another that means another concept which is basically presented in the circuit design or while we are doing these architectural designs of digital integrated circuits. So, that is the hazards. What is hazards? So, hazards means is some unwanted signals. Okay. That means actually how one digital circuit works. We gave some of the input and then we based on the logic or based on the that means operation of the function, we know that this will be my expected output. But sometimes it happens that though we have done the logic or that means though we have not that means done the logic means suppose some missing of the logic, it creates some unwanted signal presented at the output. So, those type of that means those type of condition is known as hazards in digital integrated circuits. So, here I just wrote that thing as hazards in digital circuits or digital integrated circuit, both are same. Okay. So, the first thing is that what is hazards? Hazards are changes in the output when changes should not logically occur, means this is unwanted changes. So, there are three type of that means hazards are present, which is the first one is static hazard, then dynamic hazard, then function hazards. So, what are these hazards, when this is occurring and how you can remove, we will see in today's lecture. Okay. So, first we will talk about what is static hazards. So, static hazard is the situation where and when one input variable changes, the output changes momentarily before stabilizing to the correct value. There are two type of static hazards, one is the static 1 hazards, another one is static 0 hazards. So, what is static hazard? Static hazard says that sometimes it happens that your that means one input you are changing, okay, but the output is not, that means it is before stabilization, that means whatever is the correct value or whatever what I said, that whenever we put some of the input or the test vectors as the input to the for testing of the corresponding circuit, the output behavior also I know or the pattern of the output behavior also we know that this is the expected behavior for that particular circuit. But sometimes it does not happen, the results which I will get, though the proper correct value, it does not stabilize to that, it gives you some unwanted signal, some unwanted values on that for some corresponding positions. So, whenever you are getting the output is currently 1, but after the input changes the output momentarily changes to 0 before settling to 1, that type of hazard is known as static 1 hazard. Just the opposite one, that means the output is currently 0, but after the input changes the output momentarily changes to 1 before the settling to 0, that is static 0 hazards. Mean what? You will get some of the glitch Glitch means what? Some unwanted signal or spurious signal which is present at the output. So, the static hazards mostly it is formed in two level AND OR logic based on a sum of products expression, and there will be no static 0 hazards. Conversely, there will be no static 1 hazards in an OR AND implementation of a product of sum expression. The most commonly used method to eliminate the static hazard is to add redundant logic. Okay. So, how to add redundant logic, that also we will see. Suppose what it says that AND OR logic, in AND OR logic there will be no static 0 hazard, but static 1 hazard will be there. Just the opposite in OR AND implementation or this product of sum, AND OR means sum of product, okay. And then this OR AND means this product of sum. So, in this particular two case, this static 1 hazards occurs. Static 1 hazard occurs what? Static 1 in sum of product, and in product of sum this static 0 hazard. So, static 1 hazard, if I consider this particular example, okay. So, this particular type of hazard is usually due to a NOT gate within the logic. We can see the effects of the delay in the circuit. Now, suppose if I take the corresponding example of this, so at that time we can visualize the corresponding logic 1 hazard at the output, which is y. So, let us start with that. So, this suppose consider one equation which where is y equals to a bar and b bar, c bar and with d, and a b c and then b c d bar. Then what is the output when the input is equals to a equals to 1, b equals to 1, c equals to 1 and d equals to 1. When all these a, b, c, d are 1, so at that time the y output value is 1. Again, when all the, that means this a, b, d are 1, c is 0, y is again 1. What happens as c changes from 1 to 0? So, in these two particular case, you see in both the case y is 1 as c is changing from 1 to 0. If you just see, suppose if I consider the corresponding changes in this. So, input C is changing, input C is basically at 1. Okay. So, then AND 3 output means this is the AND 3 output. C is 1, A, B, D all are 1, right. So, A, B, D all are 1 means C is 1. So, in AND gate what happens? If the other input are 1, then it depends upon the corresponding value of the other input. Okay. Here if you see, this is the AND output, this is the third gate, okay, or I have just numbered it as 3. So, here what is connected? B, C, sorry, A, then B and C. A, B, C is connected to 3. So, A and B is 1 means what? It is depending on the values of C. Okay. So, here you see, so as this is 1, this is also 1. Then not 5 output. What is not 5 output? Not 5 is the just the inversion of C. So, inversion of C means as this is 1, so this will be 0. Then AND 2 output. What is AND 2 output? AND 2 output is C bar into D. So, D is 1, C one of the input is 0 means this C output 2 output, as long as C is 0, this output will be 0. Okay. So, as long as this N output, sorry, not output from the 5 C bar is 0, and output 2 is also 0. Then what will be the corresponding OR output? OR output means here what I am considering, this is basically, if I do not just consider these two. So, if I consider only this 2 and 3, 2 and 3 if we just considering and then calculate this OR output, final OR. So, at that time 2 and 3 means ORing of this 2 and 3 means 1 and 0, this is 1. Okay. Then input C is changed to 0 and 3 is after some time it will be 0, because this has some delay, this gate has some delay. So, after that time now this is basically coming to 0 because of this change in the C. Then NOT gate also it will have some, that means delay, and then again it is becoming 1 over here. That means the changes is occurring at this particular time, but because of the gate delay after some time this is the AND output is changing to 0 and the NOT output is basically changing to 1. Okay. So, as long as this is 0, so this is not that case. So, whenever this NOT output is 1, whenever this NOT output is 1, so AND gate N2 output will be what? N2 output is 1 and D is 1, means what? So, after that again after some time N2 output is at 0 and OR output is considering this 1 and 0, that is 1. Okay. So, here you consider that after this particular time period, this AND gate now it will try to change. Why this N2 is having extra delay element over here? Because of this is passing 2 gates. So, till now because of this NOT gate it is getting the delay. So, whenever this output is changing, so after some time now this N2 will be changed. Okay. So, N2 is now changed to because of this NOT which is changing to 1. So, 1 and 1 this will be 1. So, OR output this will be again changed to what? This N3 and N2. So, which is this 0 over here and 1 over here, sorry, yeah, sorry, this 0 over here and then 0 for 0, this will be up to after this will be 0. Okay. Then again after some time what will happen, because of this particular terms. So, this time period it will be remain at 0, after that again it will be changed to 1. Why? Because OR is passing through 3 delay element, that means 1, then 2, then 3. Means what? If you just see, so this is at level 4, right. So, here you see N2 is basically changed to 1 and N3 is 0. So, OR will be changed at what? OR will be changed after some delay related to OR gate, which is this. That means, after again some time it is changing to, which is this 1 value of this. So, it is arriving this 1 and 0, then again it is becoming 1. So, that means, but this particular 0 it will not happen. Why this will not happen? If you see in both the case the y should be 1. So, that means y will continue its value. to 1, but because of this gate delay, I am getting 1 0 which is happening in between of this. So, this is basically the glitch, okay, and this is static 1 hazard. Why? Because though the output should remain 1, but it is momentarily changes to 0. So, that is why this is static 1 hazard which is happening in case of sum of product. The same example, if you just, that means same kind of example, if you take for product of sum, that means OR AND case. So, at that time you will get this as static 0 hazard. Okay. So, how to deal with this hazard? So, this hazard can be dealt with in two ways. Either match the delay causing the hazard with another delay by adding a buffer gate which delay a path without changing the state. That means what? Here in this particular path, as because of this particular NOT gate this is happening. So, add here some of the other delay buffer over here, so that these two paths became balanced. So, if these two paths became balanced, so at that time you will not get any delay over here. The same things if you just take another thing is that what I said, that you put some redundant logic. Okay. So, redundant logic means suppose the corresponding Carnot map, if you just, that means for the corresponding logic, if you just put the expression of y into a Carnot map. So, at that time you will get the expression, or you can find out the expression based on this, right. So, here you see the glitch is due to the gate delays and should not happen logically. So, does it occurs as C changes from 0 to 1? No. If only it will occur whenever this C is basically changing from 1 to 0. For 0 to 1 change, there will not be any glitch. Okay. So, why no? Because as gate 3 turns on before the gate 2 turns off. Okay. That means gate 2 turns off means what is gate 3? Because this gate is turning on before of this gate 2 is turned on. Why? That is why what I said, as there is no balanced path in between. So, that is why it is happening. Okay. So, after that what I can do? So, this particular terms, that means this expression is basically creating the hazards. So, for that reason, to reduce that, what I have to do? I have to take here what is happening. So, that means all the ones are basically covered. So, that means this is the minimal logical expression you can take from the Carnot map, right. But if you take another extra of this term, that means another extra of this combination. So, if you just take that, this particular glitch will be minimized. So, you can take that, that means you can take this example, or you can just calculate the corresponding expression for that, and then you can just simulate in any simulator, and then you can check whether you are getting any corresponding error for that, that means any glitch or not. So, that means then what is the meaning of that is, this kind of things unintentionally it may happen in your particular circuit, and when it will be occurred, whenever you will do timing simulation. For the functional simulation, you will not be, this kind of things will not be recognized, okay, or that cannot be noticed. Only when you are doing this timing simulation, at the time this kind of this logic, these hazards will be noticeable. So, that is why whenever you are getting violation at that means you are getting this some kind of glitch or this hazard. So, at that time by putting these two kind of things you can remove the hazards. So, one of the way is that what? One of the way is that you make the path balanced, another thing is that you just add some redundant logic to nullify the corresponding glitch which is occurring. Okay. So, then you this is the, that means in static hazard we can have two hazards, one is static, that means this static 1 and another one is static 0. Then dynamic hazard, what is dynamic hazard? Dynamic hazard is the possibility of an output changing more than once as a result of a single input change. Dynamic hazard often occur in larger circuit where there are different routes to the outputs. If each route has a different delay, then it quickly becomes clear that there is the potential for changing output values that differ from the required or expected output. As an example, a logic circuit is meant to change output state from 1 to 0, but instead changes from 1 to 0, then 1 and finally rests at the correct values to 0. This is a dynamic hazard. So, then if we take the example of dynamic hazard, then you see, suppose this is the, that means there is several paths which are basically going from input to the output. Okay. So, here you see we now as we shall see, dynamic hazard requires a more complex method to resolve. So, consider all inputs at logic 0, then B changes to logic 1, that means all to A, C to 0 and B changes, initially A, B, C all are 0 and then this B changes to logic 1. What will happen? So, initially this all is 0. So, all this 0 means OR is 0. So, this is 1, this is 1. Okay. Then after that what is happening? So, 1 and then 0, this is 1, this is 1 over here and 1 over here. So, this is 1, then this is 0, this is 1, 0, this is 0, this is 1, this is 1. Okay. Now, next what will happen? Now, next what I did, B is changed to 1. So, B is changed to 1 means what? Now, initially this was 1. Okay. So, after some time this will be 1, sorry, this will be 0, but for that particular time whatever is the gate delay. So, during that time it will be remained as 1 1. Okay. So, then again if I just see, then again it is changing to 1. Okay. That means, now 1 is basically continued. So, at that time it will become 0, here 0 is continued, here 0 is continued. So, 1 will be continued. So, here it will get at this particular point what it will get? It will get 0 0 1. Why 0 0? Because this gate is also having some delay. So, initially this 0 is passes through 0 0. So, 1 1 here, 1 1 here, considering that. Okay. So, now whenever this 1 is now continuing, so now it will try to affect this as 0 and this as 1. Okay. And because of this now this output is basically changing accordingly. Then next it will become 0 0, this will become 1 1, this all are 1. So, now based on that 1 1 0, 1 1 0, 0 0 1, 1 1 1. Okay. Then again this will be, now this will be just try to continues. Okay. Whenever these particular terms all, that means are becoming, that means for 5 clock cycle, if I just consider, at that time you see, though this 1 will be continued, but I am getting this as 0. Why? Because this particular, because of this inversion at the B. So, 1, 2, 3, 4, after 4 level, this delay, the corresponding changes because of this is tries to reflect at the output. Okay. So, if you just see, what can be seen is that when B changes from 0 to 1, there is a sequence of changes within the gates which leads to the output changing from 1 to 0, which is correct. At one point, gates 2 and 7 changes simultaneously. That means, gate 2 changes from 0 to 1 and gate 7 changes from 1 to 0, which keeps the output at 1. Okay. But if the AND gate 7 change just before the AND gate 2, then the OR gate 5 would see a 2 zeros on its input, driving the output low before the gate 2 turned on, and this would affect the following effect. That means, if you just try to continue, at that time I will get 0, then again as there are 2 inverter in these 2 particular case. So, based on this we will get the following hazards. It is not that only one glitch I am getting the glitch twice. Okay. Twice because of 2 inverter I have used over here. This is not only because of this B as well as for the C, that means for 3 and 6 both are basically try to changes in this particular circuit, and I will get this kind of dynamic hazard. So, in static hazard what is happening? That is because of one gate, that one glitch I am getting. So, here at the output, if multiple paths are basically affecting, at that time I can get multiple gates, and that is why this is known as dynamic hazards. Okay. So, then the third thing is that function hazards. So, what is function hazards? Function hazards are non-solvable hazards which occurs when more than one input variable changes at the same time. Hazards such as function hazards cannot be logically eliminated as the problem lies with the actual specification in the circuit. The only real way to avoid such problem is to restrict the changing of input variables so that only one input should change at any given time. These restrictions are not always possible. For instance, let us imagine some logic circuit that has 2 input and one input is used for clock signal and another is connected to a random noise source that we use to measure. So, it should be clear that restriction in this case, suppose you consider one of this particular function. Okay. So, in both the inputs are at 0, then the output is 0. If both the inputs is 0, at the time what will be? So, 0 means this AND gate, whatever is the other input, this is 0, this is 0, so this is 0. Okay. If they both then changes to 1 simultaneously, then the output should stay at 0, but delays may cause a short time when the output goes to 1. Okay. Means what? When both are 0, this is 0. If now from 0 to 1, if I change, so at that time what will happen? Sometimes after sometimes this will be coming to this and this will be coming to this. So, depend during that particular time, this will be, so this is changed to 1, okay, and what is this value? This value was 0. After that, at that time this value was 1, whatever delay I am getting over here. That means, so whenever there is a change, this value is now changed to 1, but for the corresponding delay for this, whatever is the delay amount, till then it is 1. So, at that time I am getting 1 over here, the same thing is happening over here and 1 over here. So, at that time I am getting 1 over here. Any of the input if I change to 1, so this will remain at 1 depending on the corresponding delay of these two inverters. Okay. So, this is basically known as the function hazard. Okay. So, how to, that means deal with this? We can deal with this considering that do not care things. So, in Carnot map, whenever there is no such state available, so at that time we have to consider that as a do not care. Okay. So, if we just take the corresponding position as do not care, at that time this kind of function hazards will not be occurred. Okay. So, suppose one of the example if I take, so at that time you see that all the, that means this is the corresponding truth table of one particular circuit, right. So, now y 1 or phi 1, so phi 1 is represented as something like this. Okay. So, now for this each of the expression is something like this. So, whenever I am getting this expression, so at that time this is a complicated expression and does not take into account the fact that 6 of the 16 input combination can never exist as they are never generated. These are this 10 to 15. What is that? This 10 to 15, this 10 to 15 they have been never generated. Okay. So, if we regenerate the Carnot map, we do not care in this position, we will have, so that means for this do not care position, if we do not just fill with this corresponding do not care, that means this position, if I just do not fill with this do not care, so at that time the expression will be something like this. Okay. And from here you just note that not all x's are grouped, this is fine, but there is a potential hazard in the solution, but it cannot possibly occur. So, these two expression if you just compare, that means if you do not consider this do not cares and if you consider the do not care, at that time the two expression is different. So, that means because of considering this inverters over here, okay, so you may get the glitch in this particular expression. Okay. So, to remove that you just group with do not care. So, which will, that means you just put some extra logic to remove those glitches. Okay. So, this is the, that means end of hazard. Okay. And this is this setup time violation, hold time violation, then this glitch. Whenever you will actually work on the digital VLSI design or this integrated circuit design, so at that time this you will get or this you will face in your circuit. So, this is just to give the overview of that if this kind of things happen, so at that time this is the logic which you can think of to remove this. This is not only the case, suppose if you are getting hold time violation. Okay. So, hold time violation how you can remove? You can put some extra buffers to the clock period, so that as we said, as we see that if you put extra buffer, so at that time you can avoid the clock bump, that means the hold time violation. Okay. So, now suppose we are getting setup time violation. So, at that time how we can reduce or how you can remove that setup time violation. So, those kind of, that is not at all a part of your optimization, that means doing the logical optimization I can remove, it is not that thing. You can do, but if you are not getting that, so at that time some of the tips or tricks are there by which you can remove those setup time violation or hold time violation. For a simpler circuit, this type of violation or this is not that much important or that will not be seen. But whenever you are working on a complex circuit design, so at that time this timing analysis is one of the very much important issue, because so many violation you will get. Here we are not considering any memory based design, right. Suppose memory based design, so it whenever we are suppose fetching the data from the memory and then again storing the data in the memory. So, those memory based design again it creates very much problem in the sense of getting the violations. In one clock cycle you have to write it, or you have to write it first, then you can read. So, this kind of things you have to be remembered. So, there are several, that means tips or techniques are available in digital integrated circuit design. It is not at all possible to cover up all that means all of those in this particular course, but I can just give you, or the intention, proper intention of this course is to that there are so many things. This is just to show you the path that okay, this is the way you can go. Now, you can, if you are interested any of this path, you can explore it, and it has a very deeper way. Okay. So, that is why I cannot in this particular course, that means within the time limit I cannot go into the deeper in each of this path. I am just giving you the direction in this path. Now, if you are interested, then please let me know. Okay. More onto this, then we will discuss it via discussion forum. Okay. That we can do, or else I will provide you my email ID. If you are interested, then also you please let me know via my email ID. But the thing is that whenever you are working in this digital VLSI design, it is one of the very interesting topics or interesting that means subject, not only for this learning. All the circuits are basically dependent on this digital VLSI circuit design, mostly, not all, mostly they are dependent on this digital signal processing. Nowadays all the things are basically digitally processed. So, that is why this course is very much, that means if you are this particular direction is very much interesting, and people are working a lot in this each of this particular path or in each of this direction, and it is not for one that to get mastery in each of this direction. So, if you are interested for any of the direction, then please go through that. How much help you need from me? Obviously or surely I will do that. With that, I am just thanking you all for attending the course. So, this is the end of this. This is the last lecture of this course. So, thank you all.